Day 3, topic number 3, intermolecular forces and properties. So we have covered 1 and 2. We are moving into number 3 now. We know that number 3 is basically just labeled as intermolecular forces. However, they've actually clumped a lot of stuff together into this. Most recently, we have been spending our time in Unit 11 talking about intermolecular forces like hydrogen bonding, London forces, dipole-dipole interactions, and how they affect boiling point, vapor pressure, etc. So this stuff should still be really, really fresh. But when you split this unit open, let's take a quick look at some of the things that they're seeing here. It's actually a lot of stuff that we did in Unit 2. So let's scroll down to what we would find, where we would find it on this piece of paper here on our reference sheet. It's actually, the intermolecular forces section is actually this one right here. Gases, liquids, and solutions. Like I said, they've clumped a lot of things together here. If you actually read their description for this unit, how they break it apart, what they break it down into, they list intermolecular forces. So intermolecular forces, properties of solids, liquids, gases, ideal gases, and all the math that goes with ideal gases, the kinetic molecular theory, and then, of course, all of these wonderful equations that we see here. So when we're looking at these equations, I thought it might be nice for us to just quickly review a few of them. Remember that when we're dealing with these equations, we're assuming that the gases are under ideal conditions. So let's kind of review real quick what ideal conditions are. So in order to have ideal conditions, we want the particles far apart. So how do we make sure that particles stay far apart? That would be low pressure and high temperature, right? So if you end up raising the pressure too much, you push the molecules close together, you get what we call a real gas. Remember that a real gas, these laws are going to stop functioning, they're going to stop working. Now, when we're working through the equations that go with these, remember we have the ideal gas law right here. This can also be, because of this constant that we have right here, we can set it equal to one another. So if the conditions are changing, you can use this. It's like the super combined gas law, basically, right? And so you could change, why did I put, that should be NT, and I wrote RT. There we go. So the conditions are changing, you can really look at anything. So if they're saying the pressure's changing and the temperature's changing and the moles are changing, but they never mention volume, then you would just, erase whatever variable is not being used, okay, because it would be held constant. The second equation that we have here, this is Dalton's law. And remember that they do like Dalton's law. Both of these are actually Dalton's law. Basically, when we see this one, this was the one where, if you guys remember, I always drew the examples. We draw a bunch of different boxes. We say we have this box and we have this box, and they are combined into something like this box, and they say, like, what's the pressure, right? And so the idea is you're using a combination of these two laws right here in order to try and find that pressure. But this is basically a percentage. This is what we're doing. So we're saying that if you have a total pressure right here, and you multiply it by some fraction, so say it's 50% oxygen, well then 50% of the total pressure comes from the oxygen. Or if it was 25% hydrogen, then you say, oh, so 0.25 times the total pressure. That gives me the pressure of the individual gas. That's what we're looking at here. Where we see this one used most is actually when we are collecting gases. Remember, if you see collected over water, what you need to do is subtract out the water vapor pressure. So they'll say, oh, you collected a gas and the total pressure of the gas is 1 atmosphere because that's what the barometer is reading. So what is the pressure inside the cylinder if the water is, 10 degrees or 20 degrees or something? So you would look up, okay, the vapor pressure is contributing to the pressure inside that cylinder a little bit. So we would use this and just subtract it out. That's where we see that. We've got our what moles are equal to. This is just, mass over the molar mass here. I don't know why they like to use a capital M here. That's very confusing because the capital M is actually molarity. They're just using it in the wrong spot. So this is just grams over, I like M sub r, the relative molecular mass. I don't know why they're not adding the R on there for that. Maybe it's just a typo, I'm not sure. It's like this every year. But don't confuse that with molarity. When we're looking here, that shouldn't be any big deal. Density, mass over volume. The old kinetic energy question. This is one that I've hit you guys with many, many, many times. And this is one that people get wrong all the time. And I've made us all chant this over and over again. It's just hard to stick, but we'll do it again. The only way to change the kinetic energy is temperature, right? Sometimes people see this equation and they go, oh, smaller things must have greater kinetic energies or something like that. That's not true. This is misleading. What this equation is doing is it's telling us basically that smaller atoms move faster. Right? So if you decrease the mass of an atom, the kinetic energy is constant. So if you decrease the mass, in order for this value to stay the same, this value has to get bigger, right? So that's what this equation is really telling us. Don't interpret this as changing the mass changes the kinetic energy. It's all back to temperature for this. Okay, so this is where a lot of our math is going to be. They do include this here, which is interesting. This is, if you remember Bayes' law. So this is absorbance. These are basically constants. And that would be based off the cuvette that you're using and such. And then this is concentration. Okay, so we have absorbance and concentration. So we've talked about Bayes' law. We used our colorimeters. Make sure that you understand how all of that works there. Let's see, what else can be said about this? So we've really hit on the gas laws here, but don't forget some of the liquids and solutions portions. Don't forget to study for that. I know back at the time, this is one that I see a lot each year. I'm not sure this year with the format of the test if you're really going to have to worry about this very much. But remember kinetic molecular theory, right? When we're moving, things are moving, small things move faster, temperature increases the speed of particles, etc. And we had this graph. You might remember this. Sorry, I got a little shaky there. And then we have another one that comes up like this. And then we have another one that is coming up basically like this. And really what this graph is doing is it's giving us a couple of different conclusions. And basically there's a range of speeds, right? Each one of these is a different temp. This is high, this is low. But we see at any one of these temperatures, there is an actual range of speeds, right? Some are going really fast, some are going really slow. This is where my average is. My average is here, my average speed is here. So if we wanted to put, velocity down on this chart, we would put it there. The second thing that we should recognize is that this average that we're seeing, so here's the average at low temp, average at medium temp, average at high temp. The average is increasing with temperature. So the average increases with temperature. And then the last thing that we should see is that when we're looking at these averages, so low, medium, high in terms of speed, notice we have this axis, right? They're at different heights. So one's high, one's medium, one's low here. What does this mean, right? What we're seeing is that these speeds are more spread out than these speeds. This average is actually very, very, very dependable. The vast majority of the particles are hitting this average. Whereas in this line, this average isn't really that dependable. There are a lot of molecules that are going in speeds higher than that. So what we could say is that the average isn't as good at higher temps. So basically, like, the deviation is greater. Okay, so that's something that we could talk about there with regards to kinetic molecular theory. We can also talk about things with regards to solutions. Remember, your like dissolves like, right? So this is basically meaning that polar substances will dissolve other polar substances. We know that when solutions form, remember that water is a very polar substance. And so I have seen many, many times over the years I've seen them ask to show just water and its polarity. And I've also seen them ask to show how water attacks different molecules. So remember that this is slightly negative. These guys are going to be slightly positive. So if you have a positive ion here and a negative ion, so say we have something like salt, right? This would be NaCl, right? This is what we're looking at. We know that the water molecules are going to orient themselves like this, right? All of the negative sides are going to be moving towards that positive ion, and they will team up and they will pull it off. So remember that you will always have more solvent. So water is the solvent here, and then NaCl is the solute, and you will always have more or require more of the solute, or excuse me, the solvent, because look, you have to use so many of them to pull this apart, because this is only a slight negative. So it doesn't have the power to beat out this -1 charge. So you got to get a lot of your weaker buddies to overpower the pull that this one has here. So like dissolves like, solute, solvent. Don't forget your terms. So we have saturated and unsaturated, and we have supersaturated. So basically, saturated means that all of the particles are occupied, right? All of the water molecules are occupied. Any additional salt that you add to this mixture will just sink to the bottom. Unsaturated means that you have some free, unoccupied water or solvent molecules. So if you put more solute in there, they will dissolve. Supersaturated means that you have more dissolved than theoretically possible. So understand that as you increase temperature, I'm running out of room here, but maybe we'll put it right here. As you increase temperature, you generally, so the solubility of solids generally increases. So like at 20 degrees, you might only be able to get 5 grams of something to dissolve. But if you raise the temperature to 100 degrees, you might be able to get 50 grams to dissolve. So if you raise the temperature up, you dissolve those 50 grams, and then you let it slowly cool. If the substance stays dissolved, then you would have a supersaturated solution. There's not a lot of things that do this, so we don't see supersaturated a lot, but I would expect you guys to know the two terms of saturated and unsaturated. Those should definitely be ones that we're comfortable with. So I think this kind of takes care of everything that comes to mind right now for me in terms of properties of our solutions. Make sure that you can do molarity problems. Maybe one other problem that you might want to have down on your equation would be the old M1V1 equals M2V2 for dilutions. Because if they are asking you molarity questions here, moles per liter, you should be able to make solutions, right? So, and when you make a solution, they might ask you to dilute it or something like that. So be prepared with dilutions and the molarity. Hope this helps you guys. Make sure that you check out your assignment tonight. Oh, you know what? One other thing that might be said. I almost forgot. I just remembered. Don't forget that units are important. Pressure should be in atmospheres. Volume should be in liters. Moles. And then temperature should be in kelvins. And the reason that we do this is because over here, the R value that we're using would be this guy here. And when we're looking at that, we see that it's using liters, atmospheres, moles, and Kelvin. So make sure that you're choosing the right one. If you decide to use something else instead of atmospheres, maybe you use millimeters of mercury, which is torr, then you could use this constant. But throughout the year, we always used 0.0821. So they're giving us an extra value here. And that's fine. You could use 0.0821 or 0.08206. But that's probably it. So hopefully this helps you guys out. Talk to you later.